So, how are you guys doing today? Good, perfect. So I'll try to finish up the chapter 9 today, and then hopefully we can move on to chapter 10 next week. So we can have enough time to do the review session at least twice for second exam with the revision time first to study the exam problems. So I did the Mercury 2 surface involve like the oxidation here. We have this is what we did on Wednesday. We have a similar mechanism we can also do with the archive. We call this hydroboration. So before I get to this one, I'll tell you the two terms. So if you got some archive, meaning you have somewhere in triple bond, but if you find a triple bond in the middle, like maybe you have some groups, R groups on here and here, we call this internal archive, because you just found there's the triple bond inside in the middle. So this is what we call the internal archive here. But if you find there's the triple bond at the end, so there's no like R group, just hydrogen. So maybe this is just only one side. So you actually find the triple bond at the end. So we call this terminal archive. It's simply because you find the triple bond at the end. Makes sense, right? So it's inside, it's internal. If it's at the end, it's terminal. It's literally a terminal point. We have a similar mechanism, but this will do somewhat differently for terminal archive. But it will do the similar work like a keto, tartamol isomer. So whenever you have terminal R here. So this is R, could be anything, but I'll just replace with just one example. So it could be anything, but I'll just put simplest form right here. So like I told you on the video before, if you treat it with some acidic conditions, like water and sulfuric acid is one way. And also you treat it once again, mercury 2 sulfate here. They're going to have somewhat, the hydrolylation, but also keto, C will get to the carbonyl group here. But the way they make the carbonyl group is they're going to be more being on here, not at the end, but in the middle. So they'll form over here. So this triple will be gone, but they're going to have this one. This is this one. This is this one. And we just had that triple bond is gone. It was double bond here initially with the hydrox group, but it's a keto tartamol C that makes the carbonyl group instead now. So this is what we did last time. So this is what we call this keto tartamol will be more favored for the products other than eno one, which was this one. So you have a movement of the hydrogen that makes the keto from the eno. You can double check by watching the Wednesday one. But this is what we did. For hydroboration, it's simply the same, but slightly different on terminal. The terminal, the archive. So whenever you have this one, it's actually going to make a carbonyl group at the last carbon right here, not here. So this is more like a non-Markov-Nikov kind of rule they follow. So this is more like in the inside, so it's more in the substitute carbon, but you actually follow the one at the end. I hope you guys remember the hydroboration for the alkene is quite similar that way. So we're actually going to see the carbon group, not this one, but over here. So intermediate is so they go through this intermediate, and eventually what they get to us is so I'll write it bigger. So get through this intermediate. So you don't have to know the mechanism. It's really similar to what we saw in the chapter 8 alkene with the non-mechanical rule, but it's more like a branch form. So that's why the textbook doesn't tell you. But just keep this one here. This one goes to this one. So you see there's two hydrogen to here too, right? So obviously you had some hydrogen group, but all one again the acid. So make finally not the ketone form, but it's actually the aldehyde form. So aldehyde form is with the carbonyl group with the one R, but with the hydrogen. So difference between ketone and aldehyde is this way. See the so it made a difference. It did a similar work, which they're putting the carbonyl group on the carbons, but the position was different. When you did it with the mercury to sulfate, it's causing the more substitute carbon. But this hydroboration, as you saw already in the previous chapter for alkene, it also goes to the less substitute carbon, which will be the last one. So that's why they don't see the R group on the right side from the carbonyl groups, but here is just no R group, but just hydrogen. So that makes the final in a slightly different form, which is ketone aldehyde. This is something you can do. What you similarly did with the mercury to sulfate oxidation, but the final product would be in a slightly different form because of this mechanical rule or not mechanical rule kind of difference there. Kind of makes sense. So it's similar to what we did on alkene. So it all pretty much, so whenever you study chapter 8 and 9, you'll see a lot of similarity there. Please make sure you do the chapter 8 first, and you can move on to chapter 9. Only difference you start from the triple bond, not from the double bond. Something. Kind of makes sense, right? Okay. So I'll give you one more too. Like I told you, on Monday and Wednesday, it's very similar there. It's just a lot of things similar. So actually, whenever you do reduction here, whenever it's a good thing, reduction is you just do hydrogenation. You just put a lot of hydrogen on it. So making a lot of bond to the hydrogen that makes the compound overall a bit more reduced because the hydrogen's relativity a bit more positive in electronegativity wise. So we're gonna put a lot of hydrogen. Simply we're doing this with the palladium, charcoal, catalyst. So I don't know if you guys remember this. Whenever you have a double bond, they just go to alkane again. Okay. Just simply adding hydrogen over here. Okay. This is what we did before. Just try to think this is the triple bond now. Okay. Now you're doing with the alkyne hydrogenation here. So they goes to now the triple bond. Right? Triple bond. And now they go to double bond. And then just do one more. That's it. So you just added one more step right here. Just do the same thing. So the problem is though, whenever you do this, sometimes the chemist wants to have a alkene instead of alkane because as you already saw in chapter 8, alkene is more useful product to make even triple bond or single bond. You have some really more flexibility with changing the formation, the structure of the compound by using double bond more than triple or single bond. So sometimes they just want to stop here, but this is quite reactive here. So whenever you do this, see they do the same. So they actually go right here like so fast, so they can stop somewhere in here. Kind of makes sense, right? So if they want to stop this one, they try to find the stop right here. So it just stop and the alkene not just goes into alkene, it's still reactive. So instead of just a regular catalyst, they try to use the bit weaker ones. We call this the Lindlar's catalyst, or some people just call Lindlar catalyst. Doesn't really matter. So you don't have to know how we make this one. This is a bit more deactivated version of the regular catalyst by using lead acetate and some quinoline compounds there. So it's just working as it does, but it's just a bit more deactivated. So that's why I just stop at the alkene, just go further even more to the alkene. Kind of makes sense, right? Good. So this is the alkene. Only one thing I want you to remember, it does just stop at the alkene form. It doesn't go into further like alkane. That means you need to know there should be a double bond. So you should know this is what is a cis or trans, right? So whenever you do this one, whenever it has double bond, you need to know it's a cis or trans, right? Because double bond cannot rotate, right? So just remember this will be the cis form after you do into the catalyst treatments. This pretty much kind of makes sense because they goes into the similar metal catalyst over there, but they just added on the same side. That's why you have same hydrogen on the same phase. That means those two more like cis form, and the other organs will be all the other same phase. So this is more cis form. Okay, because that makes the double bond at the end. That's why it gives the cis form or trans form. That's important, but it goes in the same phase. Kind of makes sense that actually it makes a cis form instead of trans. But it does stop the alkene form, so that's sometimes more useful in certain conditions. Okay, so far so good. All right, so if that is the case, maybe I can give you one example. Maybe this is the, you can try to do this one over here. Then whenever you do this one with the Lindlar catalyst, this is going to be this way. Okay? It's not going to be this way. Make sense, right? Because this is where you're going to have the same side, same phase hydrogen, same phase, so it makes this. So one example. Okay, right. Makes sense, right? Yeah. Okay. Just that's it. That's really once again, I'll tell you about some mechanism and everything. All you really need to know what makes what. That's all you need to know. That makes quite really easy questions anyway. Essentially, a lot of things to just study for is really easy. Just you need to know what makes what. So there was the cis one. We have a similar one with some. Either you can use a lithium or sodium, but in textbook they use lithium here over ammonia. Okay. So in this case, I can give you the same problem here, same condition, the same reactance here. And then they're actually going to now make trans. So this is the actually also starts at the alkene, but it actually makes a trans. Okay. So this is all you need to know. I'm just gonna briefly explain why it makes trans. So whenever you have this one, it goes to this one, and there's just one electron on this carbon right there. So that makes the bond to one of the hydrogen in ammonia. Okay, so that goes to this one. So what happens to this one is over here. Okay, and then here they got this electron from this thing in cation, and they do it once more, and so they got one more. So now it has a pair of electrons left. So as you can see, when it gets the signal pair, it's negative charge again, and this one was again it takes the one of the hydrogen again in ammonia. So it also breaks. So at the end, you're going to have 2 lithium cation plus 2 helium 2. Okay. So this is why push up to this position. You don't have to know how it happens, the mechanism why, but only thing I want you to know is whenever you have alkyne groups over here, whenever you treat with the Lindlar catalyst, will give you cis alkene. Whenever you treat with some alternating method, which is either sodium or lithium with the ammonia, you get a trans. That's all you need to know. You don't have to know why exactly. But it kind of makes sense why I'm telling you this. It makes different form. Same alkane, similar alkane, but different trans or cis form. That's why we specifically pointing out this one, even though they do the similar work on the reactants. Okay. So just one more thing. Whenever it gets to this one, it is little radical form here. Just for your information, it also gives you some double bond R group attached to it. So we call this vinylic radical compound. Same, because you have something like this, but you don't have to know it. Just for your information. Okay. Just this one trans, this with the Lindlar catalyst cis. That's it. Okay. It's pretty good, right? Does it make sense? So okay, that's good. So you guys think so far so great? Yeah, I guess we're not really how easy this question we've been doing actually, because the only thing you need to know is a problem. I just how to use it. So anyway, so I'll move on to the acetylide formation. So I'm gonna tell you about a bit of nature of acetylene first, and see what we can do next. So if you have the alkyl, the anion and D, we have some. Okay, we have alkene here. We have some acetylene over here too. Acetylene, and methane over here. What they can do is they can actually behave like an acid here. Okay? That means you have this one, okay, and then they can go just to wrong way. They can go this way, so they can become anion is the hydrogen cation, right? So when it donates the protons, it behaves like an acid, right? Acid donate the protons, right? So they can do this one too. Also, you can do this one. Okay. So once again, here's hydrogen. They just release the hydrogen in form of a cation, so the have electrons goes here, so it's become anion here, benefic anion here, and then this is the same. Once it has acetylene, but it can donate the hydrogen, so it becomes acetylide. So it kind of behave like acid by donating the protons there. Okay, so whenever you do pKa value for this one, this one, this one, and this one, the pK value is about 25, I think it's 44 and 60. So lower the pKa is the stronger acidic is. So this is the strongest acid, second, and the least among those three. Because it's a lower here, second lowest, and this is highest. So this is the strongest, second strongest, the least, the weakest acid among those three. This is the pK value. Lower the pKa, stronger acid. Remember this, right? Okay. So the textbook in this chapter, it tells you about why this makes some difference in the acidity of those compounds. Is pretty simple. They talks about the hybridization. So hybrid orbitals. Obviously, for arcane, you have the sp3. You have the arcane has sp2, and the acetylene obviously sp2. And they look at the composition, like a percent composition of the s orbital. Sorry, s orbital. So it should be about 50% because it's a 1-1. Okay? This one is about 33% because it's 1-3. So it's like a 1/3. And this is about 1/4, so it'll be 25% of the s orbital on those methane, arcane, and argon, and so forth. So in this case, the reasoning is this one. Okay, by the way, this is the only thing you have to know. Which one is stronger acid among those three is arcane. That's all you need to know. This is arcane. But I'll just tell you for your information. The reason is this one. Whenever you have a higher the percent composition of s orbital among your hybrid orbitals, it's better to manage the negative charge better. Because the s orbital is the one that is more spherical shape. You know what the p orbital looks like? It's dumbbell shape, more line onto the x and y and z coordinate. But s orbital is more like the spherical shape orbital that is close to the nucleus, which is positive. So if you have a high composition, much higher in s orbital than hybrid orbital, that makes that the electrons have a more access near to the nucleus, which is positive. So if that is the true, theoretically, that electron can be more manageable near the nucleus, which is arcane, then arcane, and arcane, then arcane. So higher the s orbital in the hybrid orbital, that makes more accessibility to the nucleus because s orbital is smaller and more near to the nucleus. That makes processing. So, for example, making this one, this one, this one, this one. So whenever it donates the protons, you have an anion form of those three, right? And this is the most stable form, second stable form, the least stable form. Because like I said, it's very high in s orbital. So even though when have a like an additional electron become anion by donating the protons, they have a better management to control that excess number, that one additional electron around it is close to the nucleus in this the triple bond, because it's sp hybrid orbital, it's 50% in s orbital characteristic in that hybrid orbital. So if that anion form is more stable, they tend to, it's easier for them to lose the protons. Because if this is really unstable, right? This is very unstable by that rule I just told you, that they don't want to lose hydrogen, proton. Because they know they will become really, really unstable by losing the proton here. That's why they don't want to donate the proton that makes this one weak acid. Kind of makes sense, right? So it's relevant to the stability of an anion form of those to the acidity of those three. But once again, only thing you need to know is this one. Which one is more stronger acid among those three? That's all. The other ones is for your understanding. I think kind of makes sense in a certain point. Okay, can I move on? Why is it good? Okay, I'll just move on. All right, so why we talked about this one so a lot, not just because for the acidity, but there are certain really good example. One really good famous reaction is involved in this type of principle here. So whenever you have some acetylide anion, okay, it's negative charge. So it doesn't matter if it's hydrogen or any R groups can be here, but they will make this one negative charge by losing the protons. That makes the 5 electrons around it. But this is group 4, so that's why it's a negative charge. It's still somewhat unstable. It's still the most stable form among those three, but you know it's still unstable anyway. So anyway, so this is why they want to take the one is the some RQ halide form. Normally it's bromine or iodine. So for example, I can give you one example is this one, bromomethane here, and they just try to take the nucleus because it's negative charge. They're looking for something positive, so they kind of be like take this one, which is the nucleus in the carbon, and then goes to this one. This is it's easy to grab the paired electron because it's quite high negativity. So they becomes there's one made to this carbon now, but this will leave. But they're taking this paired electron. They leave the form in the negative charge anion form. So as you can see at the end, you're going to have R, C, triple bond, and C. Now this carbon right here, right? This carbon. Okay. So now you just you can actually add the RQ groups to the way you can find that the lone pair, which in your acetyl halide anion, so it can attack, and that makes this bromine or maybe iodine or as leaving groups, and they just can have this new product over here. Okay. Kind of makes sense, right? So I'll give you maybe one more. So maybe you can have some this one, okay, and then do the same thing here. The text here, the leave here, okay. So then now it's going to be these two over here, right? That's it. So basically, what it happens here is whenever you do this one, they attach this RQ group to where you can find the double bond, and this leaves. So whenever you have that with the R, so this is the R prime, this is R double prime, this is maybe two different R groups here, and you have a CH2, and then maybe just bromine here. Only thing you have to do, just remove this one and put this one in this way. So R C triple bond, and just now is to C H2 R. That's all you need to know. Just whenever you have this form, okay, I'll give you one example here. So whenever you have this form over here, okay, and then you have say this one, okay, and then just try to remove this one, okay, then CH3, C triple bond, CH2, CH2, CH3. That's it. That's all you need to know. That really, yeah. Once again, you don't have to know the mechanism. You just need to know what makes what. Simply just, right there. That's it. Okay. Looks good, right? So just one more thing I want you to remember is to make the acetylide anion from the acetylene or any other argues with the triple bond, you need to have a very strong base. We normally use sodium amide with some solution. So, and then they takes this one out, okay, and they become ammonia with the sodium. So they become acetylide anion pairing with the sodium cation, and now it has ammonia. This one grabs the hydrogen, so this pair of electron goes on here. So that's why it makes the negative charge on this carbon that makes your acetylide anion. So they pair with the sodium cation, which were coming from sodium amide, and this part has become ammonia again, because this NH2 grab a hydrogen, now become more neutralized. Okay. So this is need more. So hopefully, this is a kind of step you can just remember. So maybe anything that has the triple bond with the hydrogen, so the kind of terminal alkyne, you can have some. You can treat it with a strong base, and you can try to get some acetylide anion. They can use to make a bond with the alkyl halide, like methyl bromide, or you can bromomethane in either way. It's fine. So they can be combined with the alkyl groups. Make that bromine or iodine as a leading groups. That's what we saw before. That what happens. There's actually makes sense so far. It's okay, right? Okay. So just make sure you have this one over here. That's pretty much it for this one. I really don't think I'll put it on the exam for sure, but just for your information, this putting the alkyl group to your acetylide anion is only for primary alkyl halide. So that means whenever you have like a bromocyclohexane, that is actually secondary. This is not primary; it's a secondary. The alkyl halide here, cyclohalide here. Then it actually grabs the hydrogen instead of the bromine. So it makes the cycloalkene instead of making this one attached to your acetylide anion form. So I don't think I'll put this in the exam anyway, but just remember it only possible to attach to the primary that is like a linear form, or like here. Those are the ones that you can attach to it, not the one in the secondary or tertiary will not work on the alkylation of argon because of we just make a alkene instead of putting the alkyl group there. But I don't think I'll put in the example just for you. All right, what time is it? Oh, why? Okay. So here's the thing. If that is the case, I actually promised that I'm not gonna put any exam require more than one step mechanism. So just one step goes in, one step, and what's the product? That's most of the type of question you'll see on the exam. But what I can possibly do is I can probably do it with the extra credit here. So what I can tell you here, please tell this to your classmate too, if you're good friends. This will be exactly the same that you will see on the exam too. So I'll tell you the answer all the way. You just need to know. But it's just the series of the ones that we learn anyway. You just need to combine it. I don't think it would be a lot to memorize it. But what I can tell you is this will be just the same, exactly the same problem I'm trying to solve right now will be on exam 2. So please can advocate of your classmates to watch this video on the YouTube channel, or you can tell them to. I'll probably mention it again, maybe in the review session anyway. But just try to remember this. This is the question you receive on the exam for extra credit. Yeah. Anyway, so maybe the last part of chapter 9 is about synthetic chemistry, synthetic organic chemistry. So you're not just using one step, but maybe you can use multiple steps of the mechanism, so you can have some final product and several numbers of steps. So maybe we can try to make some bromoroalkene over here from acetylene over here. Okay. So what you can do first, you're missing numbers of carbon here. So your product has 3 carbons, but you're starting with the 2 carbons over here because acetylene. So if that is the case, first thing what you need to do is try to make it acetylide first, anion, because this is what we just did. So I'm going to treat this one. I'm going to treat this one with the same sodium amide. It's a very strong base, and then you're going to have. I'm not going to show you all the mechanism because you probably know by now why. This one, right? So you get this one, and then if that is the case, now I'm going to put it here. So now we have acetylide anion here, okay? And then we need to add 2 more carbons, right? So maybe I can say some primary alkyl bromide here. It's just like this one, okay? Makes sense, right? Okay. So then. But like I said, I'm not going to show you mechanism again, but just basically what you just need to do is this one, right? Okay. So the second step was, so you do this one first. Second step was you try to put, I'm sorry, this one. This is the second step. Now you got to here, okay? So let me redraw this one real quick. Now you're here. And now you want to make this one bromo and this one, but to do that, it's easier to make it alkene group from alkyne. So I'm gonna do it not this one, because this will make actually alkane, not alkene. So once again, what we just learned is what? Mindler-Keller's. So we can keep it in the you can keep it in the alkene form, okay? So whenever you have addition of, okay? Now you have this one added to this one, right? You good? Okay. And then lastly, what you just need to do, I hope you remember this from the chapter 8. If you just do with HX form treatments, it's the hydrobromic acid here. This will follow Markovnikov rule here. So they will try to make a carbocation on here, not here. They will attach the where it's more substitute. So they're going to bond to this one. Okay. So this is the finally you have got to this one if you just flip it. Okay. So that's pretty much it. So exactly this one. So first of all, treat the acetylene with a strong base, sodium imide, and then try to put the primary alkyl halide with the bromine here. So this acetylide will combine to this alkyl group, making this bromine leaving. And then once you have a triple bond, just treat it with not the just regular catalyst with the hydrogenation, but Lindell one, so you can stop at the alkene compounds. And then alkene compound can be utilized to put HX bromine, which is H bromine, like hydrobromic acid here, but we'll attach the where it's more substitute carbon because it follows the Markovnikov rule here. So you can have this one. This is the exactly what I'm gonna put on exam 2 as an extra credit. If you just memorize this one, you'll get an easy point for your extra credit on exam 2. Make sense, right? You good? Okay. So it just looks a lot of work, but it literally it isn't. You just need to do it step by step, and you can just build up those in a steps, and it eventually makes the desired product we design. See, so please remember this one. Once again, I'm recording this one too. You can watch this one again on the YouTube anyway. So please tell your classmates. I'll announce it next week anyway. That week anyway. It's better. So that's it for chapter 9. So chapter 10 is about the halogen, but I'll stop here. I'll move on to chapter 10 on the Monday. Okay, thank you guys.